Number 1 says glycolic acid is a monoprotic acid that dissociates in an aqueous solution as represented in the equation above. Glycolic acid is 0.6179% dissociated in a 3.85 molar solution. Sounds familiar, right? Part A says write the expression for the acid dissociation constant Ka for glycolic acid and calculate its value. This is old business. Do A. Don't peek up here.
I don't know.
And if you want to make an ice chart, that's fine. Or you can do it like this. What's that? Oh, I'm sorry. Yeah, don't peek. Don't peek. What's that? Can you figure out X? Yeah, that's what. Not yet. I'm going to calculate it, if that's what you're asking. Well, I got to calculate what X is first, because it tells me that the glycolic acid is 0.6179% dissociated. So that tells me that this doesn't dissociate very well, and that's less than 1%. So I want to find out how much of that actually breaks apart. That'll tell me what the hydrogen and the glycinate is. Now, again, if you need to make an ice chart, I don't have a problem with that. Actually, let me do that. I'll make a miniature ice chart over here. So we have 3.85 here, 0, 0, minus X, plus X. So this is that. And then my X will come from my percent dissociation. And that is our molarity for whatever X is, so now we can plug those values in.
How did you know how to? You didn't. Wait, give the percent dissociation. Isn't it supposed to be X squared?
Yes, I agree.
No, X.
If I want to find out what each one of these happens to be,
Okay.
if this dissociates, it'll form one of those and one of those. Yeah. So once you have the value for what X is, then go ahead and square it. And since we know what X is, we want to subtract it from that.
Let's see, it's a break.
Hang on, I'm splaining up here. 1.48, anybody get that?
That sounds great.
Times 10 to the negative 4. Okay. So there's your Ka. Part B, calculate the pH. Go ahead and do that. You know how to do that as well. So part B wants to know what is the pH. And again, keep your fanny out of trouble. Probably wouldn't be a bad idea to write that so you don't accidentally take the negative log of that last value that we calculated. So that's X.
What's the answer?
Patience. Approximately 1.62.
Okay, would we need to show that much for that part? Or could we just do negative y.0238?
Right here?
Yeah.
I would be pleased with that.
What?
I'd be pleased with that. I do this so that I don't accidentally plug that number in to this. So it gives me that extra second to go, hold on, that's not the number, that's the number I want. Okay. All right, part C says calculate the pH of a solution formed by dissolving 1.72 moles of solid sodium glycinate in 850 milliliters of a 3.85 molar solution. Again, this is something that we did on the last quiz. Go ahead and do that. So now we're adding a salt to this solution, right? And that's what we did on our last quiz. So adding the salt, probably want to make sure that we dissociate that and recognize that we do have a salt. Sodium does nothing. Can we still use the same ice chart that we did in the last one? Yeah, may as well. I mean, unless you're just dying to do extra work.
But it's not the same one.
Okay, again, remember that we're adding a salt to our solution that's at equilibrium. It's not just the salt alone. Okay, there's a difference. So we're adding the salt, again, in part A and B.
Wait, where'd you get, are you talking about how you put that H on it?
Okay, in part A and B, we calculated the pH of our glycolic acid solution. Now, what I'm doing in part C, okay, I'm adding the salt to this solution that already has this acid in it. So when I make my ice chart, since I'm not adding anything that has hydroxide in it, I'm just going to leave it as this. Okay? And I know a lot of people say, well, we've got this salt, can I go ahead and write OH? You can, but it's going to cause a lot more extra work.
I know, I'm confused. What are you doing? How did you go from the C2H3 thing at the top?
I thought you were supposed to put it on the left side.
Yeah,
Okay.
That's what I'm saying.
If this is the only thing that's placed in water, this has the glycolic acid already in it. It's already in there. That's part A and B. Now I'm adding this salt to this. What you're thinking of is if I start fresh with just water in it. If it's just water and there's no acid in there and I add that, we better be starting with that. Yeah, so we're adding a salt to our acidic solution. If it were just adding it to water, that's the only thing we have. Then it would go on the left, correct. But since we've already got our acidic solution and we're adding more of a common ion, just use the same equation. Unless you want to write hydroxide, but then you get to find a KV, you get to do a lot of extra work.
So it's not wrong?
It's not wrong, and if you did it right, you'll still get the same pH.
It's just a longer process than just writing up.
Yeah, it's a much longer. And don't forget that you do have an amount for this, because it even says in the question that you have was it 3.85? So we have 3.85. We have a small amount of hydrogen. I know it's 0.0238. If you want to put that in there, that's fine. And then we need to find out how much of this we have. So it's 1.72 moles in 0.85 liters, right? So it's not in a 1 liter solution. So keep your attention to that, because oftentimes I've given it to you in 1 liter, and that makes it pretty easy. So that's 2.02. Everybody get that?
Yes.
Okay. So there's our, what's that? Yeah? And if we're using the 5% rule, we're not adding any hydrogen or hydroxide. So that is our concentration at equilibrium. Okay. I mean, using 5% rule, if you want to add and subtract the x's, that's fine. It's still going to come back to that. So we can plug that into our expression. And I'll rewrite it. You guys already have it on your paper. You don't have to rewrite it each time. So in this case, we're looking for the hydrogen, and we have 2.02 and 3.85, which is equal to the Ka that we found earlier, -4. So bring that up, multiply that. So then your hydrogen. Now, could we use Henderson-Hasselbalch on this equation? Well, you haven't watched the video yet. It's fun. You'll love it. You don't have to use it. That's just an option if you know what to do. If you're not 100% sure, I would not use it. You're never required to use it. So 2.82, you guys get that? Times 10 to the -4. Yay, nay? Yes, no? Okay. So that's our hydrogen concentration, so we can find our pH by taking the negative log of that, since that is our hydrogen. .55. Okay. Did anybody have hydroxide in this and still come up with 3.55 for your pH? Okay. So the pH of our buffer is 3.55. I'm going to go ahead and put that in the corner there.
Why?
Just nice to have. What's that?
We just added stuff.
This is our buffer solution right here.
No, we just added stuff.
We created our buffer.
Okay.
Yeah, in other words, a buffer has an acid and its conjugate base and relatively high concentrations of that. That depends on how much hydrogen you're going to add. I mean, these are high values, so that pleases me.
What was the first pH of the calculation for?
That was just for the glycolic acid alone,
Okay.
which was 1.262.
Yeah.
Yeah, you would never use that as a buffer. Just an acid alone. Okay, so now that we've got our buffer, let's go ahead and do part. D says 0.75 moles of HCl is added to 850 milliliters of the solution created in part C. So, what is HCl? What is it? Hydrochloric acid. What's important about hydrochloric acid?
Strong acid.
Very good. It's a strong acid, so it dissociates completely. And again, we don't care about the chlorine, but we do care about the hydrogen. And it says that we have 0.75 moles of it in 850 milliliters. So we got to find out what the molarity of that is. So what we're doing is we're adding a strong acid to our buffer. And we hope that it's going to absorb all that hydrogen. So based on the information that we had on part C, do we want to write this ice chart with hydrogen or with hydroxide in it? Hydrogen, yeah. Make sure whatever strong I'm adding, that has to be on the product side. And we had, was that 2.02? Can't remember, I don't think. Was that 2.02?
Yeah.
Okay. And then we just found the 0.882 molarity of that, and this was 3.85. Okay. So we want to do a complete ice chart whenever we add a strong acid or a strong base to this. Again, whichever value is smaller, that one goes to 0. So what is my value for X for this? 0.882, very good. So we'll subtract 0.882 on this side, and we will add it to the other side. And don't forget, if you subtract it on one side, you have to add it to the other side. We can't just lose it. And then let's find out what these values are. So this is 1.138, we'll say. 4.732. and then the hydrogen goes to 0, and then equilibrium is reestablished, and that's what we're going to solve for. So far it looks like it's an okay buffer because it was able to absorb all the hydrogen. Now again, if you have a scenario or a situation where the hydrogen or the hydroxide, whichever strong you're adding, is a higher concentration or a higher molarity than the thing you're reacting with, this becomes a very simple problem. Once you subtract them out, whatever the concentration of the hydrogen or hydroxide is, take the negative log. Okay? But here we have to use our expression. So our Ka, we'll go ahead and plug these in. So we have our hydrogen times this. And there is no 5% rule with buffers. And that's all equal to 1.48 times 10 to the negative 4. So multiply that on both sides, divide that on both sides. And so our hydrogen is equal to 1.48 times 10 to the negative 4 times 4.732 or 1.138. What's that? What's the matter? Anybody get 6.15?
Times 10 to the negative 4?
Yeah. Okay.
Yeah.
Negative 5. Well, I got negative 4. Anybody get that number? Negative 4?
Yeah. 4.
Okay. And then finding pH. So negative log 3.21. Okay. Now, the original pH was 3.55. Here it was 3.21. Not too bad. If I just added this concentration to water, wow, that would be
Wait, why are you doing that?
I want to show you what the pH could be. It would be less than 1. Okay, so this is pretty good. It changed it only by about 0.3 and some change, where if I just added this amount of hydrogen, it would be really close to 0. Okay, and you can have negative pHs as well. So this did a nice job. It didn't change it by a factor of 3.5, so to speak, but it only changed it by about 0.3. Number 2 says a new question. An aqueous solution contains dissolved C6H5NH3Cl and C6H5NH2. The concentration of the C6H5NH2 is 0.5 molar and the pH is 4.2. For the C6H5NH2, the Kb value is equal to 3.8 times 10 to the negative 10. Part A says, calculate the concentration of the C6H5NH3 plus 1 in this buffer solution. So since you know this is a buffer solution, we should have high concentrations of both the acid and the base, whatever they happen to be. However, do we have a salt in this problem?
Yeah.
Yeah, we do. And hopefully you can recognize that you do have a salt. Because to make a buffer, you have to have either an acid with a salt or a base with a salt. And in this problem, we actually have a base with a salt. So the first thing that we need to do is dissociate the salt so we can ignore the part that doesn't do anything. Just like in the last quiz, I think I gave you guys a salt. Don't ever show the salt or components of the salt within the ice chart. So C3Cl, that's our salt. Because at the end of this is our metal, this is our non-metal. Making sure that you remember your 6 strong acids and your strong bases. This doesn't do anything to chlorine, so we want to break that off. And it makes that. So chlorine does nothing. So this is one of our components here. And then the other thing is C6H5NH2, which acts like a base. How do I know that the C6H5NH2 acts like a base? Because you're given a Kb value. Okay? So since we know it acts like a base, and if you read on to the next part of the question, part B, are we adding a strong acid or a strong base to this buffer solution? A base. So we want to have hydroxide on the product side. Okay? So since hydroxide's on the product side, be sure that you put the thing that acts like an acid with the hydroxide. And how would I know that acts like an acid, or it is an acid? How do I know that's the acid where that is not?
Wait.
Okay?
Why is
How do I know that's an acid where that's a base?
H3?
Okay? Well, there's a couple reasons. You were given a Kb value for that, so you know that's a base. This has one more hydrogen than this. So the one more hydrogen tells me, hey, if I gain a hydrogen, okay, and that's what the mechanism is, if I take that hydrogen off and put it on here, I make that, plus the thing that remains is hydroxide. Okay? So that was given to me in the problem. So you're given two things. You're given this and that in the problem, recognizing that that's a salt.
So if you did the little equation thing with the CH5 and H3, if you did the thing where you take off a hydrogen, is that basically what you did?
I didn't take any hydrogens off. I just haven't put this in yet. So to go back, we would take a hydrogen off of here and then add it to that to make water and this. If
Is
that's,
it the same as the last one where we put it at the end instead of the beginning?
I don't know. What do you?
The last one.
They're talking about like when they first thought like it was just water in there and you added it in, so you led with your.
Oh.
Oh, okay.
No, we wouldn't want to lead with our salt.
No, I'm saying so
Okay.
put it at the end of it.
In this case, the hydrogen you're saying, put it.
I'm just saying you take that and put it in. Instead of
Take this.
No,
This.
that.
And put it at the end.
Yes.
Yes.
Okay.
Okay. And what the question is asking is, what is the concentration of that? Isn't that cool? So you think. Okay. So we start off with nothing there. So we can't say that we have a zero here because this says it's a buffer solution. So that means we've got to have some amounts for this and for this. That's why you have a question mark. Or whatever variable you find to be your favorite there. This, I think we got a value for 0.5. Okay, so we'll do an ice chart. This will decrease by x, this will increase by x, and this will increase by x, but we really don't care. We're going to use 5% rule. Do we know the concentration for the hydroxide at equilibrium? Yeah, we do. How do we know that?
Because those pH is 4.20.
There you go. So your POH is equal to, now if I'm doing my math right, 9.8. So to find the hydroxide, we take the anti-log of the negative good. So there's a lot of great concepts in this question. Wouldn't you agree? Wes, you all right over there? You just mumbling away. 1.58 times 10 to the negative 10? Is that what you were saying over there? Okay. So we know what the value for x is, don't we? But we really just want to know what that is. Now, if you want to take this value and subtract it from 0.5, is that going to make any difference?
No.
Not in the big picture. Okay. So really, we're looking for this. And here, let me get rid of that question mark because I know that bothers a lot of you out there. And you know who you are. So we're looking for that. And obviously, water doesn't do anything. So let's write our expression. And am I writing a Ka or a Kb? Kb, very good, because I have hydroxide. Again, if you have hydroxide, Kb, you have hydrogen, Ka. So our hydroxide. Next time I'll try to use an organic compound that doesn't have so many letters and subscripts. Okay, so we know this. Actually, times 10 to the negative 10. We don't know this. This is our question that we're asking about. We know this to be 0.5, and do we know the value for kV?
Yeah.
Yeah, it's given in the problem. So it is 3.8 times 10 to the negative 10. Okay, so we have 3 of the 4 components. This problem becomes really simple now. So we're going to multiply 0.5 by both sides. That. So it's not even asking for pH. How boring is that? So C6H5. Times 0.5 over 1.58. Anybody get a number? Is it 1.20? Good. Okay, so there's your concentration. And that's a pretty good number that we would want to have or expect, because again, we have 0.5 here, so for it to be a good buffer, we have to have a value that's relatively high. None of this times 10 to the negative 10 stuff. Okay, that's not going to happen. So now that we've got our concentration for part B, we're going to add a strong base to it. Now, if you want to get started on that, knock your socks off. Can I use this same ice chart?
Yes.
Okay, I'm going to say that. 1.2 molar of this hydroxide. Do we know how much of that we have? We know we have 4 grams. Okay, so we have to change that. So 4 grams of sodium hydroxide. And the molar mass for sodium hydroxide, and if you use this enough, you'll memorize it. And is that in 1 liter? I can't remember that. Yeah, good. Yeah, that makes it easy. So 0.1 molar. Anybody else get that? Okay, so the hydroxide is a 0.1 molar. And did I exceed the buffer capacity in this? No. So that means that I have enough of this to absorb all the hydroxide. Okay, you might have a homework problem where the buffer capacity is exceeded. So this is my value for X. And then add it to this side. And 1.10 here. The hydroxide goes to 0, then equilibrium is reestablished, and that's what we're going to solve for. And I just erased the kV, which was really special. Okay, so we'll solve for the hydroxide there. And no 5% rule, we don't need it. And it was equal to 3.8. Yeah, thank you. Times 10 to the negative 10. So multiply 0.6, divide the 1.1. Could we use Henderson-Hasselbalch on this?
No.
Oh yeah, because we have concentrations for both our acid and our base, or however you want to phrase that. And so 2.07, anybody get that?
Yeah.
Times 10 to the negative 10. So that's your hydroxide. So pH is 14 minus negative log of the hydroxide. Okay. 4.32. I can't remember what the pH was before. What was the pH in the previous? 4.20, that was given. So that's not too bad. That's pretty good. Now, if you wanted to use the Henderson-Hasselbalch equation. All right, now, the Henderson-Hasselbalch equation for POH is this, where it's pKb plus the log of, is HB on top? Yeah. So HB over B. Okay. So looking at this, who is my HB plus? That one, right? Because it has one more hydrogen than my base. Now, if I wanted to find the pH for this, this gets really fancy. I can do 14 minus pKb of the log. Okay, we can incorporate. Doesn't that look like fun?
That looks like a mess.
That is awesome. So then, let's go negative log of 3.8. Was it 3.8? And you guys believe me, hanging me here dry, aren't you? Times 10 to the negative 10. Plus the log of my HB is that, so 1.10 over 0.6. And I'd be willing to bet the farm it equals that. Okay. So the option is, if you want to do it this way or the old-fashioned way, it's okay.
Old-fashioned way.
Okay. That's cool. All right, giddy up.
We don't have to do that. Like,
You never have to do this, no.
Good.
No. If you're comfortable with the way that I taught you for the last 14 weeks, you're good to go.